Welcome to Operating Systems Lecture 30. Right. So last time we were talking about page replacement algorithms, and we looked at random, we looked at FIFO. We also looked at a hypothetical algorithm which we called min, which is, let's say, the optimal, which assumed the knowledge of future. And we said that assuming that past is equal to future, LRU is the best approximation of min. So assuming that past approximates the future, LRU approximates min. But then we said LRU is too difficult to implement because you need to put a timestamp on every memory access, and recall that memory accesses are on the hit path and they need to execute on very fast. So putting a timestamp on every memory access is a very expensive operation, so it's not really practical in general. So implementing perfect LRU is hard because you need to put a timestamp on every memory access, and that needs to be on the hit path. So putting a timestamp on every memory access is not possible. Instead, clock is a 1-bit approximation to LRU, where the timestamp is just 1 bit, which says whether it was accessed or not. So there's just 1 bit, and this bit is stored in the page table entry. Recall that there were these extra bits in the page table entry, and so one of them is used on the x86 hardware to represent the access bit. And so the hardware basically sets the access bit. So the first time the page, if the access bit was 0 and the page gets accessed, then the access bit becomes 1. If the access bit is already 1 and the page gets accessed, nothing happens, right? It just remains 1. So that's a 1-bit approximation to LRU, and we said that that basically, so we basically use FIFO, except that we use this 1 bit to distinguish between pages that were accessed recently and that were not accessed recently. Pages that were accessed recently are not replaced, they are instead moved to the other list for the first time. So you basically examine these pages in FIFO order, and if you see a page that has been accessed recently, you clear its access bit, indicating that it has been moved to the lower level. But if you see a page in the lower level in FIFO order, then you basically evict it, the first page you see it, right? So that's another way to think about it is that it's a clock, and you keep a pointer to the last page that you accessed, and you move the clock in one direction, and these clocks have access bits 0, something like this. And each time you come across a page whose access bit is set, you set it to 0, and if you see something which is already 0, you evict it, right? And because you are storing the pointer, the next time you run the page replacement algorithm, you're going to start from where you left off. So it looks like FIFO in that sense, right? Basically, you're just advancing the pointer from where it was last time. What is the logic behind setting the access bit from 1 to 0?
As in, shouldn't we set all the 1 bits to 0 and cover the whole revolution?
Well, I mean, basically the idea is that if a page is 1, then I set it to 0, so that I want to observe whether it is, so I have seen it once, and now the next time I am more interested in seeing whether it was accessed in the last revolution or not. Right? I don't want to carry over information from 10 revolutions behind. I'm not interested. I'm only interested in knowing whether it was accessed in the last revolution or not. And to be able to do that, I need to clear it so that it gets set again.
So can't we traverse a whole revolution and set all ones to 0?
Can't we traverse all of them and set all of them from 1 to 0? I mean, this is in some sense doing that, except that it's not a global operation. You're just going in a sequential way. I mean, the net effect is similar, right? You're just going one by one, and whichever you see as 1, you set it to 0, and so each page is getting in equal time to get accessed, which is 1 revolution, or roughly equal time, on average, because it's all symmetric anyways, right? But of course we said that if the number of pages is really large, then the time that a page gets to prove that it's actually being accessed recently may be too large for what you need, and so you may want to use a 2-hand clock, and just say that the leading hand is going to clear the bit, and the trailing hand is going to evict. So the leading hand just clears the bits if it finds a 1, and the trailing hand evicts if it finds a 0. And so for a page to not get evicted, the page should have been accessed between the leading hand and the trailing hand. That's the only way the page will survive eviction. It will not be able to, it will survive the pass. And so and so you can tune that by using, and so this angle is fixed between the leading edge and the trailing edge. That's, let's call that theta. So this angle is fixed, and depending on how much time you want to give to a page to really allow it to be called accessed recently, you will choose theta. If you choose theta to be too large, you're basically you're giving it the page more time. If you choose theta to be too small, then you're giving page too less time. And the extreme cases are if theta is equal to 0, you're actually not giving the page any time at all, and it's just FIFO actually at that point. And if you make theta 0 to 360, then you are basically back to one hand clock, right? All right. So there are some. The clock algorithm is fairly successful in the sense that it's actually being used for many years to do page replacement, and here are some more extensions to the clock algorithm that are usually used. So one is replace multiple pages at once. So instead of replacing one page at a time, so each time you get a page fault, you are actually just obliged to replace one page. Instead of replacing one page, you may want to replace multiple pages at once, so that you'd save. So firstly, if there are any 30 pages, you can write all of them in a batch to the disk. And so as we know that a disk is dominated by the seek and the latency time, rotational latency, it's better to write a bunch of pages together rather than one page at a time. Also, it saves. So yeah, so I think it's basically about saving the number of writes that you can have. Another sort of straightforward extension to the clock algorithm is what's called the nth chance algorithm. So one way to think about the clock algorithm is it's also called the second chance algorithm, where pages that have been accessed recently are given a second chance, right? So you basically process all your pages in FIFO order, but if you see that a page has been accessed recently, you give it a second chance, which means you set it to 0 and you give it another chance to basically prove itself once again, right? And if it's able to prove itself again, which means it gets accessed recently, you give it yet another chance. But if it's not able to get accessed recently, then it gets evicted. So it's a second chance algorithm. The nth chance algorithm is just a straightforward extension. You say instead of giving it 2 chances, give it n chances. So the idea is that each time you see, so you go along the clock, you see 1 bit, you set the counter. So you maintain a counter with every page, which says how many times you have seen this page to be not accessed, right? So in how many rounds have you seen this page to be not accessed? And each time you see a 1 bit in that page, you clear the counter to 0. So basically means it was just accessed recently, so the counter is 0. If you see it as 0, then you increment the counter. You don't replace it immediately, you increment the counter by 1, right? And when the counter reaches n, which is where n is the nth chance of n, then you replace it, right? So let me just write the nth chance algorithm. Let's make it more clear. Counter per page on sweep by the clock hand. If you see a 1, then clear counter. If you see a 0, then increment n, increment counter, right? Also, if counter equals 1, replace or evict. All right. So in other words, the clock algorithm, as we've seen it, the second chance algorithm is just nth chance with n is equal to 1. The first time you see it as a 0, you increment the counter, and the counter becomes equal to 1, and you replace it. Did I say 1? It should be n. Okay. So the clock algorithm is not the nth chance with n equal to 1, but if you want to give a page more chances to basically prove itself, then you increment n. The higher you have, the larger n the n is, the more revolutions you have to make before you actually evict a page. You have to actually see the page as not accessed for at least n revolutions before you actually evict it. So you're giving a page more chances in that sense. Also, the higher the n, the closer you are to LRU, right? So basically, let's say n was equal to 1000, you're basically saying that this page has not been accessed 1000 times, and so this is the best candidate to get evicted, right? On the other hand, if there's a page that was accessed in the last 1000 revolutions, before, will get priority over. So you're getting more fine grained. You're distinguishing between a page that was accessed 1,000 times and a page that was accessed, that was not accessed across 1,000 revolutions, and that was not a page that was not accessed across 900 revolutions, let's say, right? So the higher the n, the more fine grained you are getting. You are distinguishing between pages that have not been accessed 1,000 times for 1,000 revolutions, and a page that has not been accessed for 900 revolutions. So the higher the n, the more closer you are getting to LRU. The downside is the more work you have to do to find a page to replace, right? Okay. All right. So if this is, so the nth chance algorithm with a large n is one way to approximate LRU, but in general, clock algorithm works just as well as LRU, because LRU is anyways an approximation to the what's optimal, and clock algorithm is an approximation to LRU, and in general it works good enough. So you don't need to do these nth chance nth chance or kind of things, or you don't need to have a very large n to basically have good hit ratios, right? The whole point of doing all this is basically to have good hit ratios without having too much overhead on your hit path and also on the miss path. One common thing that's done is treat dirty pages preferentially over clean pages. So when you're doing replacement, you can imagine that if you evict a dirty page, you'll have to do more work, because dirty page eviction requires a write to the disk. A clean page eviction does not require a write to the disk. So keeping this in mind, you may want to give more priority to your dirty pages. So you may say, oh, this is a dirty page, let me give it more priority over your clean page. So if I have a choice between dirty and a clean page, I'll probably pick the clean page to evict. All right. So one common thing that's sometimes done is use the nth chance algorithm with n is equal to 1, 2 for dirty pages, and n is equal to 1 for clean pages. Right. So evict the clean page the first time you see it not accessed. Evict the dirty page the second time you see it not accessed. All right. Also in this scenario, you make it clean when n is equal to 1, right? So let's say you went through that page and you figured out that it has not been accessed in the last revolution. So you don't evict it immediately, but you also say that let's just write it back to disk, so that by the time hopefully by the time I come to it next, it becomes clean. And this write back to the disk can be done in an asynchronous fashion, in a batched fashion. So lots of dirty pages can be collected together and written back. So if a page has not been seen accessed in the last revolution, which is at n is equal to 1 for the dirty page, you can just put it in your queue to be written back to the disk, and because it's likely to get replaced in future. There's a some indication to use there. So you make it clean at n is equal to 1 and you replace it at n is equal to 2. Right? For clean pages, you can just replace it at n is equal to 1. So just one example of where nth chance algorithm is actually used and to preferentially treat dirty pages over clean pages. All right. So let's just understand where LRU works and where LRU doesn't work. Right. So LRU works very well. Basically, LRU captures the recency, how recently you have accessed the page, and in general, our workloads are actually have a lot of similarity between past and future, and so recency works. But here's an example. Here's a common example of a pattern where LRU does not work. So let's say you have some physical memory M, and you are accessing a set of pages P such that P is greater than M. Right? So you're going, let's say accessing 1, 2, 3 dot P, and you're just accessing these pages in a, let's say repeatedly in a cyclic manner, 1, 2, 3, 4, 5, 6 till P, and then you come back to 1 and so on. Right? Now in this case, let's see what happens with LRU. So you access 1, 2, 3, 4, 5, 6 till M, all of them are misses in the first iteration, and but all of them get into M. So your M basically becomes 1 dot M minus 1, or 1 dot M actually. Then you access M plus 1, and which is the page that you replace? 1, right? So you replace 1 and you put M plus 1 here, and you replace 2 and put M plus 2 here, and so on, right? Till let's say P and P minus 1, and then you access 1 again. The problem is that 1 the page that you replaced is also the page that you are going to access. So here's a case where past is not equal to future. The page that was accessed least recently is actually the page that will be accessed closest in future, right? In this sense, in this case, instead of replacing 1, it would have been in fact better to replace the page m, because m is the page that is going to be accessed latest in future, right? So basically, instead of LRU, perhaps MRU, most recently used, which is completely counterintuitive, would have worked in this example workload. Just pick the page that was most recently used. That's the page that's going to be accessed farthest in the future, and so that's going to have some hit rate. LRU in this workload will have completely zero hit rate. All the accesses will be misses. And this kind of a pattern is actually quite common. For example, a process going through an array of just scanning its array linearly, or going through its data structure like a tree or whatever. So basically, any linear scan and repeated is quite a common scenario in real workloads, and that's why we have to worry about it. Okay. So what happens with a scan? So this kind of a workload is also called a scan. And notice that the worst performance, or the LRU seems to perform the worst if p was equal to just 1 greater than m. So let's say p was equal to m plus 1. So you basically, for the m plus 1th page, you replace the first page, whereas the next page you're going to access is 1. So you're basically replacing the page that's most likely to be accessed next, right? And so this kind of pattern is called a scan. And the problem with scan is that, let's say, typically your operating system will have multiple processes running, or multiple threads running, or at least multiple access patterns. So there's somebody who is accessing it in a linear scan, and there are other parts of the program that are just accessing it in a very differential way. That means they're always accessing the same locations again and again. But one scan can actually pollute the cache by bringing in lots of cold pages into your cache. So all your hot pages get flushed out, and the cold pages, because of the scan, get placed in your cache, and so it causes a lot of misses. Ideally, it would have been nice if your algorithm could figure out that, hey, this is a scan, and so I don't need to do any caching for these pages, right? Anyway, these are going to be misses, and rather I should focus on doing caching. I should focus on retaining my hot pages. All these p pages are anyways cold pages, so let them have misses. These hot pages shouldn't get polluted because of the cold pages. And the reason this problem is occurring is because LRU is only looking at recency. It's only looking at what was the least recently used and throwing it out. It's not looking at frequency at all. So if there is some hot page which is getting accessed 100 times, and there's this cold page that was just accessed once recently, the cold page gets preference over the hot page just because it was accessed more recently. So ideally, we should have some way of figuring out, some way of combining frequency also with recency. All right. So there's an algorithm called least frequently used, but this is also a very impractical algorithm. You basically say what is the least frequently used page, but the problem with this is that it has a long memory. A page that was accessed a lot of times 1 hour back may just keep polluting your cache, which is not typically your typical workloads will perform badly in LFU. So typically you combine recency and frequency in some way, and so LRU is not used in its plain form, and there are examples of algorithms which extend either LRU. So there's an algorithm called 2Q, there's an algorithm called clock with adaptive replacement, and so on, which basically and there are many others. So most operating systems will implement some variant of LRU that is scan resistant, right? So because scans are common workload patterns, and any good algorithm should also be scan resistant, and LRU is not. Okay. All right. So one algorithm that I just to give you an flavor is called LRUK. Here the idea is that you don't evict the page that was least recently used. For each page you track the last k references. Right, and then you evict the page which has the least timestamp for the kth reference in the past. So in LRU we were just looking at the last reference for the last access. Instead of the last timestamp for the last access, you look for the last timestamp for the last kth access, and that's the one you replace. So you know, LRUK is basically giving some preference to frequency, and but the LRUK is also very expensive to implement in the context of an operating system, but LRU2 is used in databases. Right? Just to know. Okay. All right. So now let's talk about how something like how a cache replacement algorithm is implemented, and there are two choices: global versus local, or per process. Should I do replacement for all the processes as considered as one pool, or should I do replacement for each process separately? Right. So there are two options. I can consider the memory used by all the processes as one global pool, and so if one process page faults, I consider this whole pool as one replacement pool, and I can take page from some other process to serve this process. And the other cases I have separate pools per process. Right. So clearly if you use global, then you have more optimality overall. If you have per process quotas of memory, then it's possible that one process is underutilizing its memory and another process is overcommitting its memory, and so you know you have artificial barriers, and that's causing extra page faults than you actually need to. On the other hand, global replacement has this problem that one process can actually run away with all the memory, causing all other processes to perform very poorly, right? So a typical security attack or you know performance attack on a machine could be that you spawn a process and it just touches a lot of memory, right, and just keeps touching a lot of memory, and so it's just bringing in a lot of memory, so all other processes sees much less memory than actually available on the system, right. And so you know the operating system has to balance optimality or efficiency with some level of fairness. Okay. So in practice you basically use, so in practice there are two things that are typically used. One is you know either they use completely global replacement, so you know just global replacement assuming you have a very large memory pool and your caching parameters are correct, you know it's very hard for one process to actually pollute the cache of other processes. The other way to do it is basically have per process pools. So you have per process quotas. Let's say you know I have a quota for let's say this is my complete memory, and I have some quota for process P1 and I have another quota for process P2, right. And then I basically if process P2 is taking lots of page faults, then slowly I will move this barrier in one direction or the other. So if I find out that P2 is taking lots of page faults and P1 is underutilizing its memory, then slowly maybe on the order of minutes I will basically figure out and try to move this this quota allocation one direction or the other. The important thing to note there is that the movement of this allocation boundary is much slower than the boundary than the actual page replacement rate, right. So that gives you both some level of fairness and yet not too much inefficiency, right. So it gives you fairness because P2 gets P1 gets isolated from P2 to some extent. At the same time, if the operating system figures out that P2 actually needs a lot of memory and P1 doesn't need that much memory, then there is some adjustment at a coarser time level granularity to make to account for that. All right. Okay. Okay. Good. All right. So. Okay. So this is So we have discussed demand paging, and we have said that pages are brought as and when they are required, and there is page replacement algorithm going on. And in general, if a process takes a page fault, it has to wait for a disk request, and while the disk is actually serving this process, you will probably run another process, and so the cost of page faults actually gets hidden, and the page faults in some sense become free, right? But let's see what happens if memory gets overcommitted, right. So let's say the sum total of all the memory that's required, or all the active memory that's required by all these processes, is greater than the physical memory that you actually have, right. So let's say there's processes running and you have physical memory, but the total amount of memory is smaller than the amount of physical memory that you have. This is greater than this. So this is, let's say, the active set, active pages of all these processes, and this is the physical memory, and this is greater, right. So what's likely to happen is processes are likely to take lots of page faults. So let's say this process takes a page fault. It's likely that it will go to the disk and it will replace one of these pages, and these pages, and so one of the pages that are actually resident is going to be replaced, and because all these pages are active, most likely you will replace an active page. And so because you have replaced an active page, very soon you will get another page fault because of that replacement. And so eventually what will happen is all these processes will just keep taking page faults, right. So one process takes page fault, it replaces the other process's page, that process takes a page fault, it replaces this process's page or its own pages, and so you're basically spending a lot of time on page faults. And so what's happening at this point is that the system is spending a lot of time taking page faults and reading and writing pages from the disk and not actually executing useful instructions. The program was written to execute useful instructions, but these instructions are just page faulting, and for no fault of theirs. It's actually the operating system that was trying to play tricks under the carpet, providing a very fancy illusion of a large address space with performance latency of physical memory. But at this point what has happened is you have an address space, all right, but the access latency is not of physical memory. The access latency now becomes of the disk, right. So each memory access now becomes disk latency access at this point, and so this situation is called thrashing, right. So at this point the operating system is thrashing, or your computer system is actually thrashing, which means most of the time is actually being spent on reading and writing data to and from the disk and not actually executing useful instructions. And you may have seen this in real life, in practice. If you spawn too many processes, you may have seen that sometimes the computer becomes really slow, depending on if your memory is not big enough to handle that many processes, and let's say your flickering light for your hard disk access is continuously flickering, which means the hard disk is continuously being read and written to, but the computer system as a whole seems to be very slow, and really at that point your system is thrashing, right. Okay, so typically what do you do to resolve this situation in practice? You close some processes, right. And so why do you expect that if you close some processes things become better? Because if you close some processes, then they will reduce the set of active pages. So some processes are not active, so their pages have been removed from the process, and now the set of active pages fits in the physical memory, and so at this point you can now start executing from physical memory speed back again. All right. Okay, so an operating system automatically also can try at least to do the same thing. So how does an operating system deal with thrashing? So let's say dealing with thrashing. Well, if just one process is causing all the thrashing, then there's nothing the operating system can do about it. That one process is actually accessing so much memory or so many active pages that it cannot fit in the physical memory, and there's nothing the operating system can do about it. The maximum it can do is schedule that process less often so that other processes are not affected, or maybe even kill that process, right. So those are the only two options if just one process is causing all the problem. The more common case is that the sum total of all the running processes is causing all the problem, and so in that case the operating system can do something like that. It can figure out which process is using how much memory and then schedule the processes in groups. So have two groups, one is active processes and other inactive processes, and so at a time you will have only some set of processes in the active processes, and make sure that the sum of all the active memory usage of those processes is smaller or comfortably smaller than the size of the physical memory, right. Okay. So basically have a set of active processes and have a set of inactive processes, and keep moving processes from active to inactive, right, and make sure that some of sum of pages, active pages inside of the active processes is less than physical memory, or comfortably less than physical memory. The scheduler only schedules the active processes at a time. The inactive processes remain in the sleeping or suspended state, or even in the ready state, they are not actually brought up and started to run. So it's the scheduler that's playing, playing in consonance with your virtual memory subsystem to figure out, which processes should be run at this point, so that the system doesn't start thrashing at this point. Okay. So now question is, how do I figure out what is the size of the active pages of a process, right? So notice I'm not just saying that how much memory is allocated in the process, that's not important. What's important is what is the set of active pages in a process, which is pages that have been actually being used by this process in an active way, right? So there's a way, so there's a term called a working set used to describe the active set of a process, and this was this term was, or this method was proposed by Peter Denning. All right, and informally, the working set of a process is the collection of pages that are actively being used by the process. All right, okay, and let's see how the working set is computed. So firstly, if you can compute the working set of every process, then it's very easy. I basically make sure that the sum of working sets of the active processes is less than physical memory, and my scheduler basically does this intelligently. Okay. Also notice that the working set of processes may change over time. So right now the process is accessing, let's say, 5 MB of has a working set of 5 MB. Some time later, let's say a few minutes later, it becomes 5 KB. So I should figure that out, and I should account for that in my scheduling algorithm. Right. So now let's first see how a working set can be computed. Right. So the working set is based on a parameter called T, and a working set is basically set of pages accessed in last T seconds, right. So if I define the working set as a set of pages that have been accessed in the last T seconds, that's one way of defining the set of active pages of a process. Notice that here again I am using recency as a criteria to distinguish between active and non-active, right. Just like in LRU I was using recency to distinguish between something that needs to be replaced or not, I am not using frequency at all, and that's also primarily because workloads typically behave in a past is equal to future manner, and so recency is more accurate guess than frequency, right. So how do I compute the set of pages that have been accessed in the last T seconds? Well, one way to do this is basically extend the clock algorithm, right. With each page keep a field called idle time per page, okay. And in the clock algorithm, if you see a 1, then set idle time to 0 of that page, right. And if you see a 0, then increment the idle time with the time elapsed since the last time you saw it, okay. And so that way you can keep track of, in an approximate manner, not completely precise, but in an approximate manner, how long this page has been idle, right. And once you have an idle time per page, your working set is basically all the pages whose idle time is greater than T, is less than T, right. Okay. So you can compute the working set in an efficient way, and you can use it. Yes, question.
So will I have to keep a record of the time elapsed for each of the page in each revolution?
So keeping the record of the time elapsed is, you can have another field, for example, idle time and last time it was set, right. And so you just have to make one computation to figure out how much time has elapsed. You know the current time, you know the last time you set it, and you basically know how much time has been set, okay. Or you can use some approximation of this. In any case, recall that this movement of the clock hand is happening on the miss path, right? And so this extra computation is not a big deal, because it's dominated by the page fault handler and the disk access and all that. So this extra computation is actually not too expensive. In this computation of the working set, nowhere have we increased the time or increased the overhead on the hit path, and that's the most important thing. All right. Okay. So so that's the working set, and using the working set you can decide which processes to keep in the active set, and that way you can prevent thrashing. All right. Okay. So here's some difficult questions for the working set idea. Well, firstly, how big should T be? What is T? Right. Well, typically tens of seconds to minutes. Right. So you use a relatively coarse-grained value of T to figure out what are the set of active pages. You're being a little conservative in this sense, and or set of active pages. You're being a little conservative to make sure that your system is actually completely devoid of thrashing. So you're completely preventing thrashing by having a large parameter for T. All right. Also, you need to handle changes in your working set. So as the working set is changing, you need to figure that out on dynamically, and based on that change the set of active processes. Also, this set of active processes is called the balance set. Balance set. And so the operating system makes sure that the sum total of the working sets of the balance set of processes is less than the size of physical memory, right? Just a term called balance set, right? And also, when you're doing all this kind of thing, you have to worry about what if processes share memory. So let's say there are two processes that share memory, then you need to worry about that as well, right? For example, one thing to do may be that these processes are considered as one unit, so they either together go into the balance set or they together go out of the balance set, right? Because otherwise, you have to account for, otherwise it's more inefficient, because shared pages are likely to be, so it's better to account for shared pages. You may want to do that. Depend if the number of shared pages is really large. If the number of shared pages is not very large, you may want to have other ways to figure out what the working sets are. Okay. All right. Another way of preventing thrashing is using the page fault frequency. So one way of preventing thrashing was using the working set approach. Another way of preventing thrashing is look at the page fault frequency of every process. Here basically you you have, let's say this is your physical memory, you have per process allocations of physical memory, all right, and also you basically maintain the page fault frequency of each process. So let's say this is the page fault frequency of process P3 and PFF of P2 and so on, right. And if you figure out that one process has a very high page fault frequency and another process has a very low page fault frequency, then you can adjust these boundaries based on that, right. So as opposed to the working set, which also has a tunable parameter called T, page fault frequency will also have some tunable parameter saying what's the threshold where you are going to move things here and there. Also, if you figure out that the sum total of all the memory pools does not fit in your main memory, then you can deactivate some processes. Okay. All right. Okay. So this is an alternate idea to working sets to be able to manage your virtual memory and to prevent thrashing. In general, thrashing was more of a problem. So this thrashing was a big problem in the early days of shared computers. So let's say in the late 70s or 80s, when we used to have large shared computers like mainframes and lots of people accessing these mainframes, then at that point you had to worry about thrashing and these kind of things to basically make sure that all the users get some level of fairness and also the maximum amount of performance that you can get out of your shared computer. with the advent of personal computers, this became less of a problem. Number one, you could, memory became cheaper, and so if you see thrashing, the best way, one way to do it is basically just add more memory, and so you get rid of much of these problems, and the OS does not need to worry about it as much as it had to worry about it in shared computers. So memory has become cheaper. The other thing is the user has more control over his system. So the user himself can manually by hand just switch off processes, but on a shared computer, nobody wants to stop his process because of the other process, right? But when you have a personal computer, the user is doing more of this management itself. So in other words, basically, in a personal computer, the balance set, it can be managed by hand by the user. All right. Okay, good. So that's all I have for the virtual memory subsystem, and next time I will start discussing about storage devices and what are the different kinds of storage devices we have, and then the kind of data structures we use on storage devices to implement abstractions like file systems. Okay. One last thing I would like to say is that the virtual memory subsystem is also used for accessing files in modern operating systems, right? So how? Well, in your virtual address space, you can so let's say this is the VA space. You can map regions of your VA space to point to files, right? And so, for example, on Unix, you can do this using the mmap system call, right? And once you do that, the programmer can now just treat this region as any other memory and do pointer dereferences on it, right? So read and write can be done directly here, and under the covers, the operating system is managing reads and writes to the disk, right? Notice that this is an alternate way of accessing files from the one that we have discussed so far. So far we have discussed ways of open, read, write, close, right? Here I have mapped the file into my address space and then just use pointers or just use my program, just consider that space like any other memory region, right? For example, I could manage a tree data structure in this space, right? And so my program doesn't need to worry about that it's actually a disk that's getting written to at the back end. To make it efficient, of course, the operating system is caching pages in physical memory, right? So it's not like every pointer dereference is going all the way to the disk. They are being handled by page faults, and pages are being brought into physical memory so that most of your operations are fast, but there are also flushing daemons and page replacement daemons that are running at the background to basically make sure that the file contents are updated. Okay. The only difference between using this virtual memory subsystem for other space and using files is that for files the user also needs some guarantees. So for example, if I write something to this address space that has been mapped, what is my, how do I know whether this actually has been written to disk or not, right? And I may need some guarantees over that. In case of virtual memory, I didn't care about any guarantee. I didn't care if the thing was written to swap or not, because when the system reboots, the swap is anyways cleared, right? The swap space is anyways cleared, but for the file I need some guarantees that it has to be written to the disk. So one way to do that is basically using, providing some kind of system calls like flush or sync. So you basically, in general when you write, there is no guarantee that the contents will be reflected on disk, but if you want to have a guarantee, then you can use an explicit system call to basically say that the contents should be flushed to disk, and they will be flushed to disk in some batched way so that it becomes efficient also, right? What are the advantages of doing file accesses using mmap over doing file accesses using read or write? Well, one advantage is I don't pay the cost of the system call. If I need to access the file, I just make a pointer dereference and that's it, right? I didn't have to do a system call which involves a trap, some kernel code getting to run, and so on. In this case, actually, I can just dereference the pointer, and assuming that the page is already mapped in my virtual address space, the operation will be logically done. Not physically done later, but logically it's done.
So but if we just read it into, if we just read the file into a character array and then we perform all the computations on that array and later write it back to the disk, so wouldn't it be the same thing?
If we read the file into a character array and write to the character array and then write it all back to the disk, won't it be the same thing? Yes, I mean, this is a way of the operating system providing you that functionality under the covers. That there you have to do it explicitly. So you have to read the whole file into your character array. So for example, if there are multiple processes who want to access the same file, so there needs to be some way of, so the file system is also giving you some sharing between multiple processes, but if you write it into a character array, then there is no sharing. For example, if there's one file that's opened by multiple processes, and so one process writes to that file, the other process can immediately read from that file, because it's a shared address space, it's a shared file system. So the file is the same. The abstraction is that it's being shared by multiple processes, but if you read it in a character array, then there's no sharing, for example, right? Also, reading from a character array into a character array requires programmer effort and programmer understanding of what it means to when to write it back and optimization. It's better to rely on the operating system to do these things for you, right? In a memory mapped environment. So you're saving the cost of a system call, number one. But is that important? Well, firstly, it's if you are going to take a disk access, then yes, this cost of the system call is not important. But if you are going to get served from the buffer cache, then the cost of saving the cost of system call is good. The other thing is, recently we have seen lots of different types of storage devices. So apart from magnetic disks that we've talked about, there are things like flash memory and other sort of persistent memory technologies that are giving you very fast sort of persistent memory. They have their own problems or quirks, but in any case they are providing alternate ways of providing secondary storage. And so accessing that, if the latency of accessing that kind of secondary storage is very small, then the cost of actually doing the system call becomes large. So let's say hypothetically speaking, the disk was as fast as memory, right? In that case, using the read-write system call to access the disk is very wasteful. You would want to access it with the same interface as you access memory, which is just pointer dereferences, right? And so mmap is a nice elegant way of being able to do that. All right.
If the file changes in the disk due to some other process, do we reload the page?
So we are going to discuss this in the file system discussion, but let's say this is a disk. The disk is, the operating system sits on top of the disk, right? So no process can touch the disk directly. So if there's a process, if there are two processes that are accessing the disk, the operating system is maintaining synchronization between them, firstly. And so if this one changes something, it changes both in the buffer cache and in the disk. And so later, if somebody reads it, he'll read the latest value from the disk. Okay. So the abstraction is that of a shared file. Right. So the operating system is responsible for doing synchronization, which means that there shouldn't be any race conditions on access of the buffer cache. There shouldn't be any race conditions on access to the disk. But at the same time, the abstraction is that of a common file. It's not, the abstraction is not of two independent files. All right. Okay. Let's stop here and start our discussion on file systems next lecture.